Hey guys, for this how-to video, we're going to go over question 2.23. In this problem, we are given a wall of a specific thickness with a certain thermal conductivity, and it has uniform volumetric heat generation. We're setting that to Q dot. There is convection at both surfaces, and the temperature of the fluid is 30 C. The temperature distribution in the wall is given by this equation here, defining these parameters. And we're going to be asked to sketch the temperature distribution in the wall, find the volumetric heat generation in the wall, determine the heat fluxes at each wall, determine the convection coefficient at the boundary conditions, and obtain an expression for heat flux distribution, as well as turn off the heat generation source and determine what the rate of change of energy stored in the wall is, as well as what the temperature the wall will get to when Q dot is equal to 0 and how much energy will be removed from the wall per unit area. Starting with our sketch, I just plotted this in Desmos. So we have this equation here that defines the temperature distribution throughout the wall, and we're given certain points here that help us determine things in the wall. These two red lines going by are the edges of the wall, which is plus L on this side and minus L over this here. And we just know that the wall is filled in here in this shaded red region. For part B, we're going to look to find the volumetric heat generation within the wall. So in order to do that, we're starting with the heat equation for Cartesian coordinates and simplifying it using our assumptions here. So 1D heat diffusion, constant properties, steady state and neglect, radiation. We know 1D heat diffusion, so we can get rid of the y and z terms. Constant properties, so we're going to take the x out front, and steady state, so we're getting rid of the stored energy term. In this simplified version, we know that Q dot is equal to negative K times the second derivative of temperature with respect to X. And we know the temperature distribution is given by this equation here. So when taking the second derivative of it, we get negative K is equal, or times 2C is equal to Q dot. Plugging this in, we get that Q dot is equal to 200,000 watts per meter cubed. Part C is looking for the heat fluxes at both surfaces. So in order to do that, we're taking the 1D heat equation, and which is Q double prime is equal to negative K times dt dx. We know T is this equation here, so taking the first derivative of it this time, we get that Q double prime is equal to negative K times B plus 2Cx. And now we're going to solve for this at each boundary condition, so at plus L and at minus L. Plugging all these variables in with 0.03 meters for plus L and negative 0.03 meters for minus L, we get 7,000 watts per meter cubed squared and minus 5,000 watts per meter squared, respectively. Part D, we are looking for convection coefficients at plus L and minus L. So we know that Q convection is equal to H delta T. We know what Q convection is at the boundary conditions that are solved above, so we know that H at plus L and H at minus L needs to be equal to Q at plus L, or Q double prime plus L and Q double prime at minus L, divided by delta T for both of these. We can get the temperature at these points given this Desmos plot that we have, where at this boundary condition, minus L, we know that the temperature is 74 C, and at plus L, we know the temperature is 62 C. So plugging these in, we get 218 0.75 watts per meter squared Kelvin for plus L, and 113.64 watts per meter squared Kelvin for minus L. Part E is looking for the heat flux distribution. And so we're going to take the equation here that we were given, or that we solved for rather, and set this equal to 0. So we want to know what the where the heat flux distribution, or where the heat flux is equal to 0 within our distribution. And so solving this equation for 0, we get that x is equal to minus 0.005 meters, which in our temperature distribution plot is the maximum. So this is what we would expect by taking the derivative and solving for it at 0. Now we're going to turn off the temperature, or the heat generation. And at this point, we know that if we turn the heat generation off, all of the heat generation is going to be turned into stored energy. So at this instant, we get that E double prime ST is equal to negative 200,000 watts per meter cubed. When trying to determine how much energy must be removed, we're first going to look at what the temperature of the wall will reach at steady state. And when it, after the heat is already all dissipated, we know that the temperature of the wall is going to turn into the temperature of the surroundings, which is defined by 30C. So in order to figure out what the heat generation rate out of the part after the heat generation has been removed, we're going to set E out is equal to EST, which is equal to rho Cp times the integral from negative L to positive L of Ti minus T infinity times dx, where Ti is the the temperature distribution at the initial point, minus T infinity, which we know is 30C. Solving this integral as shown here and plugging all the numbers in, we get that the energy dissipated out is equal to 7 times 10 to the 6 joules per meter cubed. And that is my solution for 2.2.